We are to our last screencast in Organic Chemistry 1, and we are going to talk about oxidizing agents. Now, there are two main categories of oxidizing agents. There are reagents that contain an oxygen-oxygen bond, right? And so these include things like O2, right, or ozone, which is O3, or hydrogen peroxide, let's see, tert butyl. Trying to give you some of the common ones here. Hydro peroxide. And peroxy acids. Now, I have peroxy acids here for you. These are some common peroxy acids. They have the generic formula RCO3H, right? And so what we see here is we see a C double bond O, and then that oxygen-oxygen bond is shown there. This is a really common oxidizer. It's meta-chloroperoxybenzoic acid. The meta here just talks about the positions of these two groups. You're going to learn more about that in second semester, but I don't want you to get thrown off or panicked because you see the meta there. This a lot of times is abbreviated as MCPBA. So the trickiest thing is you've got to recognize all three of these things as synonyms when you are looking at reactions. So make sure that you know that MCPBA, that's the structure, and then you can also use meta-chloroperoxybenzoic acid as well. So that's kind of the trickiest thing there, is recognizing those names. Then the second type are reagents that contain metal oxygen bonds. Right? And so these kind of most common reagents that we're going to see are things that have either chromium generally in the oxidation state of +6, or magnesium. Sorry, I said magnesium, and I meant manganese. In the oxidation state of +7. So those are the most common ones. Common chromium reagents include things like CrO3, Na2, Cr2O7, K2Cr2O7. I want to remind you that these are just counter ions, so they're spectator ions. This is the active oxidizing complex. These all can be used as synonyms, really. We also have a pyridinium chlorochromate, which is PCC. Now, this is a more selective chromium oxidant, and we'll talk more about that in a minute. And then the most common manganese reagent is KMNO4, right, which is potassium permanganate, which you may recognize from general chemistry. Now, other oxidizing reagents that contain metals that show up a little less frequently are things like osmium tetroxide, and silver oxide. Now, let's look at oxidation reactions we're going to talk about in this chapter. So far in our journey in organic chemistry, we have talked about three functional groups. We've talked about alkenes, alkynes, and alcohols. And so what we're going to do here are we're going to talk about the types of oxidation reactions that alkenes can undergo. They can undergo epoxidation. They can to give a epoxide. They can undergo dehydroxylation to give a diol, where we have two alcohol groups. And then they can undergo an oxidative cleavage, where this bond is cut and we end up with two carbonyl compounds. Alkynes will also undergo oxidative cleavage. And then we are going to talk about alcohols, which can form ketones or aldehydes or carboxylic acids when they undergo oxidation. So this is what we're going to spend the rest of our screencast talking about. So without further ado, let's jump in and look at the epoxidation reaction. When we look at epoxidation, this is the addition of a single oxygen atom to form, so here's our single oxygen atom, to form an epoxide. Now, epoxidation is generally carried out with a peroxy acid. And again, I love that this oxygen is highlighted in red, and so you can see where it's added. Here are just some different examples where we can see epoxidation with different peroxy acids. Again, I want to remind you that MCPBA sometimes will just be shown in the reaction. Now, when we do this, we have a weak pi bond here, and that's broken, and then two new carbon-oxygen sigma bonds are formed. So let's look at that mechanism. When we look at this mechanism, it is a concerted mechanism, which means there are many steps that are happening all at once. And so I am going to write this epoxide here, and I'm going to draw it with a certain kind of geometry here, for lack of a better term, to help show this arrow movement. When I was a student, I also drew it like this. It just helped me reminded how the arrows moved. So when we look at this, here's what's going on. So these electrons for this double bond come and grab a proton here, okay? Those electrons jump on that oxygen. These electrons come down and attack that carbon. The electrons of the double bond come up and attack the oxygen. And then these electrons jump over here. And I know that's so much that's going on, and it's all going on at the same time. All the bonds are broken and all are formed in a single step. And so it's actually very, very hard to kind of think about it because everything's going on at the same time. So please don't be overwhelmed. The best thing that you can do is to write these mechanisms over and over again because it helps. It helps you remember them. Now, let's follow our bonds when we draw our two new products here. So when we look at the bond, these come over and grab a proton. So what happens then is that becomes, right, R O H, okay? And then what happens here is this bond breaks and these bonds come over here. And so now we have a double bonded oxygen there. And that's it for this molecule. So then now we have to look over here and see what's going on here. And so when we look at this, we're going to draw the bonds that aren't really involved in anything. And then look at our arrows. So this forms a new bond between this oxygen and that carbon. And so we say, great, we have a new oxygen bond here. Then we come over here and we've got a bond between this oxygen and that carbon. And so we say, great, we have a new oxygen bond there, right? And then that oxygen, right, has two lone pairs that come from this bond, and it already has two lone pairs on it. So we end up with that structure there. A few notes about this particular mechanism, right? The relative position of the substituents in the alkene is retained in the epoxide product. Right? And so what does that mean? Well, it means that this is a stereospecific reaction because the cis and trans alkenes yield different stereoisomers as products. And so a cis alkene gives an epoxide with cis substituents, and a trans alkene gives an epoxide with trans substituents. So if your alkene starts off as cis here, you're going to be cis here. If it starts off as trans here, you're going to end up being trans there. Now, let's look at the next type of oxidation reaction, which is dihydroxylation. So dihydroxylation is just the addition of two hydroxy groups to a double bond here. This forms a 1,2 diol or a glycol. So if you have these two hydroxy groups here, that's also known as a glycol. Now, depending on the reagent, the two new OH groups can either be added to the opposite side, so an anti-addition here, or to the same side here. So we are going to start out and we are going to look at the anti-addition first. So when we look at an anti-addition, this is achieved in two steps. Epoxidation, followed by a ring opening with either, right, OH minus or an acid. Now, I want to remind you of something here. You're going to see H plus, but you could also see H3O plus, or the actual acid that's used, like H2SO4, right, being used here. So you've got to really, sometimes students get confused with acids because we have so many things that can mean the same thing. And so you really have to view these as synonyms, okay? So don't let that trip you up. So when we look at this, right, we get trans 1,2 diols here, okay? And these are enantiomers. And the reason we see this is if we look at the mechanism, this goes through a normal epoxide mechanism here using MCPBA. Then we have a nucleophilic addition, and this nucleophile can attack from above or below kind of this oxygen here. So it can either attack at carbon A or carbon B, right? If it attacks at carbon A, right, then you see the oxygen here going back. And so that's where we get, this is coming forward and that's going back. And then if you attack at carbon B here, right, this goes back here and this comes forward here. So let's look now at Syn dihydroxylation. And so if we look at Syn dihydroxylation, this results when an alkene is treated with either potassium permanganate or the osmium tetraoxide here. And so we end up getting these OH groups added from the same side, right, which is that Syn. And so when we look at that, let's look at that mechanism. Let's draw our friendly cycloalkene here. And our manganese complex here. So the electrons from the manganese complex come over here and they're going to attack that carbon. The electrons from this double bond are going to come here and attack an oxygen, and those electrons are going to go on the manganese. And this occurs through a Syn addition. When this occurs, this is the intermediate that we end up with. And I always like to double check that all my electrons are good. Then what happens this complex goes through hydrolysis and produces our diol. Okay, so when we look at this for osmium, it works in much the same way. Right, so there's our osmium complex, and what we see here is that these electrons will come here and attack that carbon. These electrons will come down here and attack that oxygen, and then these electrons will go back on the osmium there. Now, this too is a Syn addition. So my two electrons look really weird there. So I'm going to go back and darken those a little bit. And then it also goes through hydrolysis. We have sodium bisulfate that is added here. And we end up with kind of that same product. There. Now, a few things is this synthesis is an older synthesis. It's not used as frequently because it doesn't give great yields, right? Now, when we talk about osmium particularly, this can also be carried out using osmium as the catalyst, right? If the oxidant, which is N-methyl morpholine in oxide, which is abbreviated as MNO, is added. So in this catalytic process here, dihydroxylation of the double bond is going to convert this osmium 8+ into a 6+ product, and then that can be reoxidized back by the NMO here. So that's a catalyst that is used pretty frequently in that Syn dihydroxylation. So let's look then at our next oxidation, which is ozonolysis. So when we look at ozonolysis, this is an oxidative cleavage of an alkene, and it breaks both the sigma and the pi bonds of the double bond, and it forms two carbonyl compounds like this. So basically, when you do this, watch where these are highlighted. Like this is the blue and that forms a ketone. This is the red. That one tends to form, well, that one forms an aldehyde because there's a hydrogen here. So whether it forms a ketone or aldehyde depends on what's attached to these carbons of the double bond. So when you predict this product, right, you can just cleave the double bond here in the middle and replace, put a double bond oxygen on each of these carbons here. You're going to see sometimes that an oxidant is shown just generically in brackets with an O. That's a pretty common way to show that something's going through oxidation. So, a couple different things that we see. We can see oxidation here with ozone, where we have some really specific examples where you can see ketones and aldehydes are formed. So let's look at this mechanism. When we come here and look at this mechanism, and we have ozone. Oops, I did not draw in my oxygen there. Don't be me, make sure you draw in your oxygen. And that's got a negative charge. I always like to go back and check all my charges. So what happens here are these electrons attack that carbon, which makes these electrons kind of pop down and attack that oxygen, and then those electrons go on to the center oxygen. And so you end up here, if we follow all of our arrows, you end up with a five-membered ring with 3 oxygen atoms. Right like that. This is called molybdenite, and it is very unstable. This rearranges into an ozonide pretty quickly. Right? And then what happens is you need to reduce the ozonide to give the carbonyl compounds. And so we use zinc and water in the presence of water, or dimethyl sulfide. And then we get our 2 byproducts. Sorry, I said 2 byproducts. We get our 2 products here. And then the byproducts, which will be either zinc hydroxide or there. So that's how we convert these alkene into carbonyl compounds. This can also be used as an opening mechanism. So ozonolysis with dienes here, or polyenes, which just means more than one double bond, results in oxidative cleavage of all the carbon-carbon bonds. And so when oxidative cleavage involves a carbon-carbon double bond that's part of a ring, the ring opens up and you end up with a single chain with 2 carbonyls at the carbons where the double bonds were originally. So here and here. Now, this is a diene, and so we can see how this opens up here. But I also want you to notice that this is also oxidized. And so we end up with 2 molecules here, right, as well. So this will go through and oxidize every double bond in a molecule. Now, this is a really valuable tool for structure determination because it helps us figure out the location of double bonds in really complex alkene structures. So that finishes up our discussion of alkenes. Let's talk about alkynes. So alkynes undergo oxidative cleavage of the sigma and pi bonds, the sigma and both pi bonds of the triple bond. And what we see here is an internal alkyne. These are oxidized to carboxylic acids, whereas a terminal alkyne gives us a carboxylic acid and then CO2 from the sp hybridized carbon-hydrogen bond here. And this proceeds by the same mechanism that we looked at previously. Now, let's talk about oxidation of alcohols, and that's our last functional group that we're going to talk about. Alcohols are oxidized to a variety of carbonyl compounds depending on the starting structure of the alcohol. So if you have a primary alcohol, right, that is going to be oxidized to either an aldehyde or a carboxylic acid by replacing either one or two of the carbon-hydrogen bonds by carbon-oxygen bonds. Okay, and so that's what we'll see here. Then secondary alcohols, which are shown here, these are oxidized to ketones by replacing one carbon-hydrogen bond with a double bond oxygen here. And then if you have a tertiary alcohol, you don't get any reaction because you don't have any carbon-hydrogen bonds to react. So you have, for alcohols to undergo oxidation, you have to have carbon-hydrogen bonds, and tertiary alcohols just don't. Now, the oxidation of alcohols to carbonyl compounds is typically carried out with chromium oxidants. So this is typically carried out by chromium oxidants, right? And so these are reduced to give chromium 3+ products. Because remember, if something's oxidized, something else is also being reduced. The ones that we see most typically are chromium oxide, right? Sodium chromate and potassium chromate. Right? And these are all strong, non-selective oxidants that are used in aqueous acid. And aqueous acid, of course, can be shown as H3O+, or sometimes it'll be shown as sulfuric acid and water, right? Those types of things. So just be able to recognize that acid. Now, another one that we're going to talk about is PCC, and that's soluble in dichloromethane, and that can be used without a strong acid present. And so it's a more selective, milder oxidant that's also used to oxidize alcohols. So let's look at this mechanism with chromium oxide. All right, so we've got our chromium. Here, and these electrons are going to come over and they're going to attack that chromium, right? And then these electrons go on the oxygen. So we end up with right? Then in the next step here, we see a proton transfer, right? Where this comes in and grabs a proton and it goes onto that oxygen there. And so now we have this molecule, and so water will come in and it will steal this proton, and then these electrons will go here, and then the chromium, the oxygen chromium bond is broken, and those electrons go up on the oxygen. This is why that carbon-hydrogen bond is so important, because if there's not a carbon-hydrogen bond here, this step doesn't happen, right? And so that's why tertiary alcohols don't react. So when this occurs, you get a, from kind of this interaction here, right? You get this molecule here. And then you also have as a byproduct. Right? Now, let's look at a primary alcohol. So this was a secondary alcohol, right? So that's a secondary alcohol, but let's look at the mechanism of a primary alcohol, because primary alcohols will be oxidized to either aldehydes or carboxylic acids depending on the reagent. So here we get a ketone, but let's look at those primary alcohols. So when we look at primary alcohols, what we're going to see here are kind of two things. If you use PCC, you get an aldehyde. If you use the chromate complex, you get a carboxylic acid. So when we look at this, right, let's look at a primary alcohol here for a mechanism, and we're just going to do a generic, we're just going to look here at a generic alcohol. And what we find is right here, okay, this goes through the same 3 steps as the mechanism on the previous slide. So same 3 steps as previous slide. Then we end up with an aldehyde here. Now, this will go through another mechanism, which you are going to learn in chapter 18. So I am just going to write down mechanism there. And what we find is that here, right, we end up with 2 alcohol groups on a single carbon. This is called a hydrate. Okay, and then what happens is that this will again go through, right, the same mechanism as the previous slide, so the slide right before this, right? And when we look at that and it goes through that same mechanism, what we see right, is that at this step, when water comes in and it steals that proton right there, and we get that same, we've got a double bond that forms there, and then the chromium goes off there. That's where we form our carboxylic acid. So when we look at this, that's where we get our carboxylic acid. Okay. I find this alcohol mechanism really fascinating because to me it has a really interesting practical application. This reaction is used and was used in early breathalyzer tests. And so potassium dichromate, for example, is orange. And when it reacts with ethanol, that's reduced to give chromium 3 sulfate, which is green, whereas ethanol is oxidized to become acetic acid. And so this color change was used in early breathalyzer tests before the digital breathalyzer test. And you can still buy disposable breathalyzer tests like this. And so how these disposable tests work is that you blow up a balloon and you attach a balloon to a tube. And this is acidic resin, and it has the chromium dichromate basically on little acidic beads, right? And then you can measure the distance that it undergoes oxidation to tell the blood alcohol level here. So for example, somebody's attached a balloon here and you can tell it's turned green, and so it's right up here at 15%. You can tell it's turned green here, so it's at 5%. It would continue to go up, and here would be 10%, right? So you can tell the different blood alcohol levels based on the color change here, which is due to the redox reaction, which I find to be a really interesting application, and I hope you do too. All right, well, this ends our journey with Organic Chemistry 1. Thank you for hanging with me. As always, if you have any questions, please feel free to stop by my office.